Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the course Analysis of Variance and Design of Experiments. So, you can recall that in the last lecture, we initiated a discussion on the development of likelihood ratio test under the setup of one-way analysis of variance model. That means there is only one variable and that is going to take different values which are going to indicate the presence of more than one independent variables in the linear regression model y equal to x beta plus epsilon. So, now in this lecture I will try to continue on the same topic, and I hope that you have revised the likelihood ratio test what we had developed earlier for the hypothesis H naught beta 1 equal to beta 2 equal to beta p. So, in this lecture now we will try to implement the same methodology under the setup of one-way analysis of variance. Right. So, we begin our lecture, but we first try to have a quick review so that we can understand what are we going to do now. Okay. So, you can recall that in the earlier lecture we had considered this model that we have the random samples from p normal populations and which are differing with respect to only the mean, and their variances are going to be the same. So, this y I j is going to indicate the random sample from the ith normal population. I goes from here 1 to p, and then j is going to take the value here, say 1 to n I. That means, we are going to get the first sample of size n 1 from the normal population with mean beta 1. Then the second sample of size n 2 from the second population with mean beta 2, and so on, right. So, in general I have denoted it, say y I j follows a normal distribution with mean beta I and variance sigma I square, and these random samples are assumed to be independent of each other. That means, the random sample from normal population number 1 is going to be indicated from the random sample which is drawn from the normal population number 2. Right. And yeah, these observations what we are going to get from each of these p population, they are the samples of size n 1, n 2, n p respectively. They are going to be expressed in the framework of y equal to x beta plus epsilon, where you can see that y is going to be like this vector, where first n 1 values are going to indicate the values corresponding to first sample, the second set of n 2 values is going to indicate the values from the second sample, and the last n p values are going to indicate the observations and variable from the normal population with mean beta p. And this coefficient vector beta is the same beta 1 beta 2 beta p, and similarly you have expressed here the random error components. So, that we did in the last lecture, and we had also discussed that how this design matrix X is going to look like. So, design matrix will look like that first n 1 rows are going to be like this, in which the first element in the first place that is going to be 1 and all other values are going to be 0, and similarly the second set of n 2 values that is going to have 0 1 values, in which the values in the second column are going to be 1 and all other are going to be 0, and similarly in the last set the values in the last column are going to be 1 and all other values are going to be 0, and where this x I j, which is the I jth element of this design matrix X, is indicating that it takes value 1 if beta I occurs in the jth observation x j, or if the effect beta I is present in x j, and it takes value 0 if effect beta I is absent in x j, and small n is indicating the sum of all the sample size, that is the total sample size, which is n 1 plus n 2 plus and P. So, obviously, in this case we had discussed that the rank of the matrix X is going to be P, that is full column rank. So, there is no problem in estimating the parameter beta or say sigma square using the maximum likelihood estimators of beta, and so expected value of y will become equal to x beta and covariance matrix of y will become sigma square I. So, this description completes the representation of a fixed effect model of full rank. Now, we are interested in developing the test for the null hypothesis H naught beta 1 equal to beta p, and we suppose this is equal to beta, that is the common value, and the alternative hypothesis is here H 1, which is at least one beta I is not equal to beta j for I not equal to j, and here both beta and sigma square both are assumed to be unknown. Now, we try to develop the likelihood ratio test for the same. So, now you can see here, when you want to develop the likelihood ratio test, first you have to define the whole parametric space and sample parametric space. So, the whole parametric space capital omega is going to be here a p plus 1 dimensional space. Why p plus 1? This p is indicating the number of beta 1, beta 2, beta p, and 1 here is indicating the parameter sigma square. So, there are altogether p plus 1 unknown parameters in capital omega. So, this omega is going to be the collection of the points on beta and sigma square, such that beta, all the values of beta, they are going to lie between minus infinity and plus infinity, right, and sigma square is lying between 0 and infinity. So, now you can see here that beta 1, beta 2, beta p and sigma square are the p plus 1 parameters in omega that are unknown, that we want to estimate, and under H naught you are assuming that all beta 1, beta 2, beta p, they are going to be the same as beta, right. So, now this value here is beta, this is only a scalar here, that you have to keep in mind, right. So, now under H naught, this whole parametric space omega will be simply reduced to a 2-dimensional space indicated by small omega, which is a collection of the points beta and sigma square. Because if you can calculate the value of beta, then you are done. So, beta is lying between minus infinity and sigma square is greater than 0, right. So, this is our sample space. Now, what is the next step? The next step is that you need to find out the likelihood function, and then you have to find out the maximum or the supremum value of this likelihood function under capital omega and under small omega, right. Although we had discussed earlier that under omega, what you have to do, you simply have to replace the values of beta and sigma square by their respective maximum likelihood estimators, because the maximum likelihood estimator of beta and sigma square have been obtained under the condition that they are going to maximize the likelihood function. But here I will try to show you that how these values are coming out to be, because now you are trying to take here the values y I j instead of here the vector y, right. So, the likelihood function under capital omega can be written here as say 1 upon 2 pi sigma square raised to the power of n by 2 exponential of minus 1 upon 2 sigma square into double summation I goes from 1 to p, j goes from 1 to n I, y I j minus beta I whole square. So, now you can see here. So, you need to observe here that here I am not using the term like y minus x beta transpose y minus x beta, but now I am trying to write down here y and x in the form of here their values, and not in the form of vectors and matrices, and that is how this term is coming here. Now, we want to find out here the value of beta I and this sigma square, such that this likelihood function is maximum. So, we try to take its log. So, the natural log of this likelihood function is given by here like this, minus n by 2 log of 2 pi sigma square minus 1 over 2 sigma square double summation I goes from 1 to p, j goes from 1 to ni, y I j minus beta I whole square, and I try to indicate by here capital L. Now, what you have to do? You need to find out here the maximum likelihood estimator of beta I and sigma square. Once you obtain them, and then try to replace here beta I by its estimator and this sigma square by its estimator, then this function likelihood function is going to be maximized. So, what we try to do? We simply try to use the same rule that we used earlier, that we try to differentiate the log likelihood with respect to beta I and sigma square and put it equal to 0. So, they will give us the normal equations, right. And when you try to solve this normal equation, we get here like this. So, you can see here that in this function, if you try to differentiate or this log likelihood, what will happen? Suppose you are trying to differentiate with respect to here beta I, then what will happen here? That this part is independent of beta I. So, this will become here 0 minus here 1 over 2 sigma square, and now you can see here you are trying to differentiate only with respect to here beta I. So, what will happen here? That you will get here only here summation j goes from here 1 to ni y I j minus beta I equal to 0, and then this 2 will come over here, right. So, basically you have to solve here the quantity j goes from here 1 to ni y I j minus beta I equal to 0, right. So, you can see here this will solve to j goes from 1 to here ni y I j minus here beta I into say here ni equal to 0, and then beta I comes out to be here 1 over ni summation j goes from 1 to here ni y I j, right. So, this is what I have written here. You can see here this is the same thing, that beta hat I will come out to be here like this. Now, what you have to understand here, that I am trying to use here a symbol here y bar I naught. How this has been written? You can see here where I am trying to write down here y I j, then I have here 3 options. I can sum over only I, sum over only j, and sum over only I and j. So, what I will try to do here, that when I am trying to take here the summation over j, then the subscript corresponding to j will be indicated by naught. So, this is going to be like here's y and then I j, but now I am taking here y bar. So, this j becomes here say here naught, and then I have here y bar I naught. Similarly, if I try to take the summation over both I and j, then this will become here y naught naught double naught, means that means summation or the average has been taken over both the subscript I and j. So, this is how I am going to indicate it by say y bar I naught. So, y bar I naught is going to simply be the maximum likelihood estimate of beta I, which is indicated here by beta hat I, right. And you can now see this is only an arithmetic mean, and this is exactly what I wanted to show you when I said that I want to develop the likelihood ratio test in the setup of specifically the one-way analysis of variance model, right. And similarly, if you try to differentiate this function with respect to here sigma square and put it equal to 0, you will get here the maximum likelihood estimate of sigma square as 1 upon n double summation I goes from 1 to p, j goes from 1 to ni, y I j minus y bar I naught whole square, right. And if you remember that means earlier you also had a similar expression, but now there is no beta, there is no x etc., and you are getting a very clear, neat and clean expression. So, these are going to be your here the maximum likelihood estimators of beta I and sigma square, and well you can go for the second order conditions, because we have used here the principle of maximum likelihood, and you will find that they are satisfied, there is no issue. So, now we have obtained here the maximum likelihood estimators for beta I and sigma I square under capital omega. And right. So, and well, if you want to see that whether these values are going to maximize the likelihood function or not, you simply have to find out here the Hessian matrix of the second order partial derivations of the log of L with respect to beta I and sigma square is negative definite when we try to take beta is equal to y bar I naught and sigma square equal to sigma square hat, and this will ensure that the likelihood function is maximized at this value. Right. So, now we have obtained the values of maximum likelihood estimates for beta I and sigma square under capital omega. So, now we can substitute these values of beta I and sigma square in the likelihood function, and since they are the maximum likelihood estimators. So, the value of the likelihood function which is obtained after substituting beta I by beta I hat and sigma square by sigma square hat is going to give the maximum value of the likelihood function over the capital omega. So, now you can see here I am simply trying to replace sigma square by sigma hat square and beta I by beta I hat, and if you simply try to simplify it, you can see here if you just substitute here the value of this sigma square hat, then this is going to be here like this one you can see here, right, and this will cancel the numerator part this thing, and then you will get here only exponential of minus n by 2, and if you try to replace it here, this will be here like this, pretty simple straightforward algebra. So, you can see here that one of the beauty of this algebra is that there is only one factor which is involving this yij or y bar I naught, and the second factor this is independent of this yij, and that is going to be the common when we are trying to find out the maximum value of the likelihood function under a small omega. So, that helps in the development of likelihood ratio test statistic. So, now we try to do the same algebra and we try to follow the same steps under a small omega, right. So, the likelihood function is going to be here like this, but now we are replacing here beta I by beta, because under H naught all beta 1, beta 2, beta p they are assumed to be the same as beta. So, this comes here beta, and there is another parameter sigma square that remains here as such in the likelihood function. So, now we try to take the log likelihood, and this comes out to be here minus n by 2 log of 2 pi sigma square minus 1 over 2 sigma square double summation I goes from 1 to p, j goes from 1 to n I y I j minus beta whole square. So, now we have to do the similar thing, that we have to find out the value of beta and sigma square for which this log likelihood is going to be maximized. So, we can just differentiate it with respect to beta, with respect to sigma square, put it equal to 0 and solve them, right. So, that is what we try to do here, and you can see here that when we are trying to differentiate the log likelihood with respect to the parameter beta, then this gives us the value of beta to be here like this, right. And in case if you are trying to differentiate it with respect to sigma square, then the value of sigma square is coming out to be here like this, and you can see here how this value of beta hat has been obtained. So, now if you try to see here, yes, if you try to differentiate here d of this log n likelihood function with respect to here beta. So, now you can see here this part is independent of beta. So, this becomes here 0 minus 1 over 2 sigma square. Now, there is no condition like I or j as it was in the case of capital omega. So, this differentiation becomes simply here twice of summation I goes from 1 to p, j goes from here 1 to n I y I j minus beta like this. And when you try to put it equal to here 0, this implies that we simply have to solve quiz part, that summation I goes from 1 to p, j goes from here 1 to ni, yij minus beta is equal to 0. And if you try to simplify it here, this becomes a summation I over j yij minus beta times here summation ij that times here 1, which is equal to here 0. And if you try to take the sum here, I goes from 1 to p and j goes from here 1 to ni, that is simply going to be here n1 plus n2 plus np, and which is equal to here n. Right. So, you can see here that this gives us the value beta is equal to 1 upon n double summation I j y I j. Right. And now you can see here, if you try to use here the same notation using the like y naught naught, then you try to write down here y I j, and now you are trying to take the average over I. So, this I becomes here now here 0 naught, and then you are trying to take the average over j. So, this j is converted into a naught. So, this becomes here y naught naught, and this is an average. So, this becomes here y bar. So, this is how I can symbolically write down this value. And so, this value of beta that you have just obtained, this is your beta hat, that is the maximum likelihood estimator of beta under a small omega, or when H naught is true, that is when all beta 1, beta 2, beta p, they are the same. So, this comes out to be here simply here the arithmetic mean of all the observations. If you try to see here, this is simply your here arithmetic mean of all the observations. Right. And when you try to differentiate the log likelihood with respect to sigma square, put it equal to 0, and just do the similar algebra, you will get here the value of sigma square hat is equal to 1 upon n double summation I goes from 1 to p, j goes from 1 to ni, y I j minus y bar naught naught whole square, where now you know that how this y bar naught naught is coming, because we are trying to replace the unknown beta by beta hat as we did in the case of likelihood ratio test. Right. Okay. So, now you also need to verify that this value of beta and sigma square, they are going to maximize the likelihood function. So, for that I will not do this algebra here, but I will leave it up to you that you try to find out the second order condition for maxima minima, and you will. So, what you have to do, you have to find on the second order derivative with respect to beta and second order derivative of the log likelihood with respect to sigma square, right. So, and then means here like this, and then you try to substitute here beta is equal to y bar 0 0, and then you try to substitute sigma square equal to sigma square hat, right, and then you will see that these conditions are satisfying, and this ensures that this value of beta and sigma square is providing the maximum of this likelihood function when beta is equal to beta hat I, and which is y bar naught naught, and sigma square hat is equal to this quantity. Right. So, now we have to find out the maximum value of the likelihood function under small omega or under H naught. Right. So, what I have to do? I simply have to write down the likelihood function, and I have to replace the value of beta by beta hat and the value of sigma square by sigma square hat, which we have obtained here. Right. So, now once you try to do it here, you can see here that this numerator part will get cancelled out with the exponent inside this exponent when you try to substitute the value of sigma square hat, and you will get here simply here exponential of minus n by 2. And here if you try to substitute the value of sigma square here hat, this value here come out to be like this, n upon twice of y double summation I over j y I j minus y bar naught naught whole square raised to the power of n by 2. Right. And now what you have to do? So, now you have obtained the maximum value of the likelihood function over the complete parametric space capital omega and the sample space small omega. And if you try to, what do you get here? If you try to look at these expressions, means you are trying to take the ratio over a small omega and capital omega, you can see here when you are trying to take the ratio over the small omega, this part is common in both the likelihood function. You can see here I have crossed it with the blue, and this part you can see here, this part, this is also common in both the expressions, this and here this. So, if you try to take the ratio, this will involve only the remaining part, which is like here double summation part. Double summation part from this maximum value of L under small omega and capital omega. So, this is what I have written here, you can see, and you can verify it here that this is the same thing what we have just obtained, that was a part of the estimate of the sigma squares. Now, you can see here these two are, they are dependent only on the sample observations. Right. So, you can compute it on the basis of given sample of data, but now the problem is how are you going to compare it? Means you want to accept or reject a hypothesis. So, you need at least one more value by which you can compare this computed value and can decide whether you are going to accept the hypothesis or not. So, for that you need to find out the distribution of this lambda. Now, so our basic objective is here that we simply want the distribution of this likelihood ratio test statistic, but the question is how. Definitely we need to use some statistical tools, some mathematical tools, some mathematical knowledge, some statistical knowledge, so that we can do it. So, now that is what now I am going to do, but I would like to make here very clear that now this is only an algebra part, the conceptual part is over, and what we have to do from the conceptual point of view, we simply have to express this statistic lambda in such a way such that it fits to the knowledge what we have based on our statistics. Now, if you ask me, I can give you here a hint. Can you see here the term in the numerator and in the denominator? You can see here that these terms are going to be like quadratic forms. The expression in the numerator and denominator, they can be expressed in the format of a quadratic form, and then y here is your random variable. So, now you need to use your knowledge about the distributions of the quadratic forms which are based on the random variable y. Now, at this moment I would request you all to recall the results that we did in the lecture number 2, where we had considered the random variable y, and then we have considered different types of results related to the quadratic form. Sometimes their distribution, sometimes the distribution of the ratios, etc. So, do you remember that if you have two quadratic forms, then under certain conditions these quadratic forms are going to follow a chi-square distribution, and if you are trying to somehow prove that both the variables are going to be independent of each other, and if you try to take the ratio of those two random variables and divide by their degrees of freedom, don't you think that you will get a distribution? Right. So, now you can see that this knowledge is going to give you a hint that how you want to proceed further. So, now our objective is very simple, that I would like to simplify this quadratic form and this quadratic form in such a way, so that I can find out the distribution of lambda easily. So, I try to do here the same type of algebra which I did in the case of likelihood ratio test, but now we are not using here the terms like y, x, beta hat, etc. Right. Do you remember that we had expressed this lambda in the format of say 1 plus q1 upon q2 raised to the power of here n by 2, and then later on minus n by 2. Right. And we have done this this q1 upon q2 format, means we have expressed this quantity in the form as a function of q1 upon q2, that help us in finding out the distribution of the statistics. So, the same thing I try to do here, that I try to consider here the quantity in the denominator, double summation y I j minus y bar naught naught whole square, and then I try to add and subtract here y bar I naught. Right. And then I try to write down here y I j minus y bar I naught plus y bar I naught minus y bar naught naught whole square. And if you try to open it, this will come out to be double summation y I j minus y bar I naught whole square plus summation over I n I times y bar I naught minus y bar naught naught whole square, plus there will be here a cross product term. But if you try to simplify that term, this will become 0. So, that is why I am not writing here in the slide. So, now you try to substitute this term here, and then try to express it in the form of 1 plus q1 upon q2. So, let us try to do it here. So, we try to rewrite this function here, and yeah, you can see here I am trying to now change the power of this bracket. This is now minus n by 2, and whereas here if you try to see, this was here n by 2. So, this numerator will become denominator and denominator will become the numerator. So, you can see here I have written here exactly the same expression which I have just obtained, divided by this quantity. And now you can see here that this quantity and this quantity, they are the same. So, if you try to simplify it here, I can write down here 1 plus this quantity divided by the quantity in the denominator, right. So, I am just expressing it here, say 1 plus q1 upon q2 is the power of here minus n by 2, where q1 is going to be your here this term, this is your here q1 and this is your here q2, right. So, this is how you can see here I have obtained it. Now, you simply have to see how you can obtain the distribution of these q1 and q2, right. So, but before I try to do, let me try to give you here some knowledge that whatever we have used here, this methodology which is giving us two functions q1 and q2, when you are trying to use the least square principle, then this q1 and q2 you will see that they will have a particular type of interpretation, and q1 there is the sum of squares due to deviation from isonot, or the sum of square between populations sum of squares, and q2 will be called as sum of squares due to error, or sum of squares within population, right, or the within population sum of squares. And this q1 plus q2, this is called as sum of square due to isonot, or it is also called as total sum of squares, and that is indicated by say SST, right. And you will see here that this q1 is also sometime called as say treatment sum of squares, right, and this is indicated by say SSTR like this. and this Q2 will be called as sum of squares SS due to error, like this one. So, I am just telling you here, so that when I am doing this part at a later stage, I will just try to give you a relevant hint, and then you will be able to understand that this is matching with the same thing that we did earlier. Now, I need to find out here the distribution of this Q1 and Q2. So, now do you remember that when we did the likelihood ratio test, we had the quantities a small q1 and a small q2, and we had converted them in a way such that small q1 and small q2 will be looking like as if they are the observed values of two random variables, capital Q1 and capital Q2. We had simply just replaced small yij by say here capital Yij, right. So, and we had proved a result that this Q1 and Q2, they will have a chi-square distribution, and they are also going to be independent. So, now do you really think that I need to do the same algebra again and again? Sometimes you get here a little bit confused, that you try to see that here the Q1 and Q2 here are like this in a different format that you done in the case of likelihood ratio test. But my thing is this, they are simply obtained by the same methodology, same principle, same rule that you followed in the case of likelihood ratio test statistic. And so, whatever the values you are getting here, they are only the particular values of those specific cases. So, now they may look different, they are the same. So, now let us move ahead, and now we have here Q1 is equal to summation I goes from 1 to p and I y bar I naught minus y bar naught whole square, and Q2 is the sum of I goes from 1 to p S I square, where S I square is the summation I goes from 1 to n I y I j minus y bar I naught whole square, and where this capital Y bar double naught, this is equal to 1 upon n summation I goes from 1 to p, j goes from 1 to n I y I j. So, this is the mean of all the observations that is related to that quantity, and similarly this is here the y bar I naught, which is 1 upon n I summation j goes from 1 to n I y I j, which is actually indicating the mean of the samples which are being obtained from the ith sample. So, you simply try to take the sample from the population and then simply try to find out their sample mean, that is all. Now, you have used this result earlier, and you have proved that Q1 upon sigma square is going to follow a chi-square distribution with p minus 1 degrees of freedom, and Q2 upon sigma square, that is going to follow a chi-square distribution with n minus p degrees of freedom. And you also had proved that those two quadratic forms are independently distributed in the theorem 6 and 7 earlier. So, I can say here directly that using those theorems I can write that Q1 upon sigma square and Q2 upon sigma square, they are independently distributed. So, now you have here one variable which is chi-square, another variable here as a chi-square, both are going to be independent of each other. So, now you can use the result about the F distribution. Do you remember that in the case of F distribution, if x is chi-square with say n1 degrees of freedom, y is chi-square with n2 degrees of freedom, and suppose both are independent, that is x and y are independently distributed, that x upon n1 divided by y upon n2, this follows a F distribution with n1 and n2 degrees of freedom. So, that is the result of what we are going to use here. So, this you can see here that this Q1 upon sigma square has got a degrees of freedom p minus 1, Q2 upon sigma square has got a degrees of freedom n minus p. So, I try to take here the Q1 upon sigma square divided by the degrees of freedom p minus 1 and Q2 upon sigma square divided by the degrees of freedom n minus p, and that is going to follow a F distribution with p minus 1 and n minus p degrees of freedom under H naught. and this is going to be a central F distribution. Right. Now, after this, the next question comes here, that the decision rule based on the likelihood ratio test statistic that we obtained in the earlier lecture was to reject the null hypothesis whenever Q1 upon Q2 is greater than C, where C was found to be like this, F 1 minus alpha with P minus 1 and n minus P degrees of freedom. Now, you have to understand one thing. When we did the likelihood ratio test, then coming from this step to this step, we use several results, several methodologies, several concepts, and then we had obtained this thing. In case if you are doing it this test for the first time, this development for the first time, you will have to do all the steps once again to explain it to anyone and to understand also. But since we already have done this algebra earlier, then do you think that we need to do the same exercise again? Certainly not. So, using that result, I am now writing here that if you try to use this result Q1 upon Q2 is greater than C, try to define a theorem for the normality of random variable and then the chi-square distribution of the random variable, try to use the theory of F distribution, and then finally, you will arrive at a conclusion that the constant which has to be determined based on the size condition of the test, that is the test has a size alpha, then the constant will come out to be here like this. So, I am now using it here directly. So, now my life has become very simple, and I will simply say here that consider this hypothesis H naught beta 1 equal to beta p, and this hypothesis is rejected if f is greater than f 1 minus alpha p minus 1 and minus p degrees of freedom. Where what is your here this f? This is the calculated value of the f statistics. Right. And now, for this thing, this is the tabulated value of the f statistics, and you can obtain its value from the tables of f distribution. And if you are trying to use any software, so you have to just find out the suitable quantile that is reflecting this critical value. Right. So, now once we have done all these things, then I can express or I can combine all the results in the form of an analysis of variance table that we popularly call as Anova table. Right. This Anova table helps us a lot when we are trying to do such analysis on the basis of given set of data, and this is very much user friendly. You see, as a user, the user may not be really interested in the algebra or the mathematical steps that you have followed. What he would like to know that what is the final outcome based on which he or she is going to take a decision. So, that is why we try to compile all the results in the form of an analysis of variance table. So, in this case where we are trying to consider the one way analysis of variance model, which is a fixed effect model, we have here these factors over here, that the source of variation is say between population, within populations, and there is going to be here a total. Now, you have to understand one thing, that when we are trying to write down here the source of variation, you will see at different places this has got a different name. Sometimes people call it sum of square due to null hypothesis, sometimes they will call it between population, but that is the same thing actually, nothing more than that. And the basic terminology like between population or within population has been derived after looking into the expressions of Q1 and Q2, right. But you need not to worry for this thing, but only thing is this, you must know So, this sum of squares Q1 is indicating the variation due to between population, and Q2 is going to indicate the within populations, and you will see that at many times this within populations variation is also called as error also, right. And the degrees of freedom related to Q1 are p minus 1, the degrees of freedom related to Q2 are n minus p. And now, in case if you try to sum them, then Q1 plus Q2 will be called as total sum of squares. Right, and in case if you try to add this degrees of freedom, this will become here n minus 1, which is that degrees of freedom associated with the total sum of squares, right. And then after that, if you try to take here the sum of squares Q1 and divided by the respective degrees of freedom, then it is called as mean square. And similarly, if you try to do the mean square for Q2, that will be Q2 upon n minus p. And then if you try to take the ratio of this mean squares due to between population and mean squares due to within population, you will get here this statistics, which is F statistics, and this follows a F distribution with p minus 1 and n minus p degrees of freedom under H naught, right. Now, one thing you will see here, and I would like to address it here very clearly, that if you try to observe here, what are you doing here? You are trying to write down the sum of squares of between population plus sum of squares due to within population is equal to total sum of squares. And they have got chi-square distribution, and their degrees of freedom are p minus 1 plus n minus p, and this total is again n minus 1. Now, you will see that whenever we recommend this analysis to be used on a real set of data, we always say that you have got here three sums of squares, sum of squares between population, within population, and total. Now, if you try to see here, what are we doing here? We are trying to sum the different sum of squares together. So, the first question comes here, how we can do it, and secondly, what to do in practice. So, now I will try to address this issue. We had already done the Fischer-Cochrane theorem. Fischer-Cochrane theorem says that that the total variation is going to be divided into orthogonal component, and their sum of squares and their degrees of freedom related to the chi-square random variable, they will be additive. Now, in this test of hypothesis, we are trying to use the Fischer-Cochrane theorem. Now, for the validity of the Fischer-Cochrane theorem, we need to know whether Q1 and Q2 are orthogonal. Yes, they are. We have proved that capital Q1 and capital Q2 are independent. And the total sum of square here is Q1 plus Q2, which has been partitioned into two independent orthogonal components, Q1 and Q2. So, this is very important for the application of Fischer-Cochrane theorem, that the sum of square should be additive, and this exact equality should hold true. This exact equality must hold true for the validity of this Fischer-Cochrane theorem. So, that is why we always say that try to compute two sum of squares manually and try to obtain the third one by subtraction. For example, if you are trying to obtain the total sum of squares and you are trying to obtain the say here between population sum of squares, then you try to obtain the within population sum of square by subtraction, that is total sum of squares minus sum of squares between populations. So, this will ensure that there is no difference in the summations of Q1n and Q2 with respect to Q1 plus Q2. And in practice what will happen that when you are trying to compute this Q1 and Q2 on the basis of some given set of data, there may be some approximation error and this equality may not really hold true. So, that is why we always advise that you try to obtain 2 quantities out of the 3 and then try to obtain the third one by subtraction. Well, this concept is going to be extended when you are trying to conduct the analysis of variance for say 2-way ANOVA model, 3-way ANOVA model and so on. So, the rule is here very simple, try to obtain all the sum of squares except one, and the remaining one has to be obtained only by the subtraction. Now, the second question is, when we discussed that why this is called as analysis of variance. So, now you can see from this table very clearly that we are trying to divide the total variation which is being measured in terms of total sum of squares into 2 orthogonal components, the sum of squares due to between population and within population, and both these quantities are going to measure the variation. Now, the total variation can be partitioned into 2 parts, that is the what is the variation due to the difference in the within the population and between the population, that is all, that is the total variation. And obviously, based on this we can take a call in terms of applications that which levels are important, which levels are not. That we will try to discuss when we come to design of experiment. Right, and that was the reason that this technique is called as analysis of variance, that we are trying to find out the sum of squares which are measuring the variation, and we are trying to compare them, or we are trying to partition them into different components, and then we are trying to compare them to know whether a factor is important or not, right. So, and here you can see here, I will not do here the algebra, but I would just like to inform you that if you try to find out the expected value of Q2 divided by n minus p, this will come out to be here sigma square, and you will see that later on we will express it as say expected value of sum of a square due to error divided by the degrees of freedom is equal to sigma square. And in case if you try to find out the expectation of Q1 divided by e minus 1, this will come out to be here sigma square is equal to like this, summation I goes from 1 to p beta I minus beta bar whole square divided by p minus 1, where beta bar is equal to 1 upon p, summation I goes from 1 to p beta I. So, you can see here that this quantity, that quantity is going to be smaller if this difference beta I minus beta bar is as small as possible, and ideally if all beta I becomes same as beta bar, that means the effect of all the populations are the same, because if you can see here, if all the populations are same like as 2 plus 2 plus 2 divided by here 3, this is going to be 2. So, that is what I am trying to say here, that by the condition beta I equal to beta bar, then definitely when all the beta 1, beta 2, beta p are the same, then they are going to be the same as beta bar, and this condition also indicates here that in this case there is no variation among the population, and whatever the variation is present in the data, that is just due to the random errors which is being measured by this quantity sum of square due to error, or this here Q2. So, now you can see that this is giving you the same answer what you expected. Okay, so, now we come to an end to this lecture, and you have now seen that up to now whatever we had done, that is now implemented on a one-way model. And believe me, This one-way model is the model which is going to be used in the analysis of the data which is coming from a particular type of design, what is called as completely randomized design. And this is going to be replicated in different ways. So, this is very important. And in this lecture, in this topic, I have given you, I have tried my best to give you the minor details also, very minute details to the best of my capacity, so that all the concepts, all the steps, they are clear in your mind. And after this, whenever I will try to take up any analysis of variance, do you think that should I repeat all these things again? Certainly not. So, this is very important for you that after this lecture, try to revise this lecture, try to understand, try to ask yourself at every step that why this is happening, and try to answer it to yourself. And once you can do it, then you try to compare it with your likelihood ratio test, because that was a more general test. There also you try to reply to yourself that why these things are happening. And after that, I can promise you, if anybody tells you in this world that this analysis of variance is difficult to understand or it is a difficult topic, I am sure that you will not agree with that opinion. The only thing is this: yes, there are several concepts which are needed, which are need to be understood, and then they have to be applied in a proper way, judicious way. And that is what I have done here, that's all. So, you try to practice, try to revise, and I will see you in the next lecture. Till then, goodbye.